Welcome to AP Physics C Mechanics, the in-depth series. Instead of just including unit videos, this is specific lesson videos about key topics. And the structure of this would be about 5 to 10 minutes of content review and 5 to 10 minutes of practice problems to apply what you've learned. So it's going to be shorter videos than usual, but it's going to go more in depth. And so this first video is going to be lesson 1.1, one-dimensional motion. So we're just going to be talking about the basic kinematic variables and then the relationships with each other. So our first topic is time, t, and what it is just the clock reading at a certain moment. The unit of it is seconds, and I'll get to why units are important in a minute. But first, time is essential, but time interval is probably going to be even more important for us. And that's just the change in time. T2 minus T1, the final time minus the initial time, also measured in seconds. Moving on to the next variable, position, which is denoted usually with an x, can be other variables as well, but it's just the relative location of an object. And so what this is going to be is measured in meters, and you just pick a point, and that's your position. Related quantity is distance, usually denoted with a d, an s, whatever. I'm going to write d for simplicity's sake because distance starts with d. It's not that important in physics. What it is the length of a path covered by an object. If this is the path covered by an object, it starts here and then goes all the way out here. The distance would just be the sum of all the length covered. Also measured in meters. One specific thing about distance is that it's always going to be positive or zero because it's a scalar. A scalar only has magnitude, no direction, and so it's just a number, like 2, pi. -3 technically, but no, usually distance is going to be positive. On the other hand, displacement, also measured in meters, is going to be what is the change in position. So kind of like how time interval is change in time, this is going to be change in position, also measured in meters. And so what it's going to be is just you take the final position, the initial position, and subtract them. So if this was your path, the shortest distance between initial and final position is going to be your displacement, delta x. Now, unlike distance, it does depend on direction. It's a vector quantity, not a scalar quantity. So it has both the magnitude and direction. We're going to talk more about vectors in lesson 1.4 when we talk about two-dimensional motion. Fun. We're upgrading from 1 dimensions. But for now, all you need to know is that it has direction. It can be negative, positive, to the east, to the west, north, south, up, down, whatever. Yeah. Now, moving on to speed. Speed is not really denoted. I'm going to use with an S because speed starts with S. Sometimes it's V with an absolute value around it. We'll get to why that is in a future video. But speed is going to be the distance traveled over time interval. And so it's d over delta t. And this is a specific type of speed called average speed. I'm going to draw a bar over that to denote average speed. Now, what are the units of this? The reason why we used units before is because now it allows us to compare these two quantities. Since it's distance over time, distance is measured in meters, time interval is measured in seconds, it's going to be meters per second. Now, if that's average speed, what's instantaneous speed? That's going to be the speed at a certain moment in time. Not over a time interval, but at a specific time. That is going to be the limit of the average speed as the time interval approaches 0. But since we know calculus, this is a calculus-based course, we're going to write it in terms of derivatives. The speed is the derivative of distance. So it's dd dt, also measured in meters per second. Just like distance, this is a scalar quantity, no direction, just a magnitude. It's always positive or 0. Velocity, on the other hand, is dependent on displacement, and so it does depend on direction. It's going to be the change in displacement over change in time. Again, the average velocity is this. Meters per second, again, because displacement is also measured in meters. Now, that means that the instantaneous velocity is going to be the derivative of displacement, also technically the derivative of position. And so it's going to be dx dt, also measured in meters per second. Whoa, big surprise. And so we're mostly going to be working with instantaneous velocity, sometimes average velocity, usually not speed, but maybe, depends on the problem. Okay, one more thing about velocity. If the velocity changes at a constant rate, the average velocity is going to be equal to the sum of two velocities over 2. And so that's just you're averaging out the two velocities. Now, this is only if velocity changes at a constant rate, which brings up a good question. Position changes at a rate, that is the velocity. Velocity is the rate of change of position. That's what a derivative means. But what is the rate of change of velocity? That is going to be acceleration. Acceleration, A, is going to be the change in velocity over time interval. And that is delta V over delta T. Now, this is average acceleration, you should know by now. Now, what are the units of this? That's going to be meters per second, that's change in velocity, over second, meters per second, or meters per second squared. Now, we also have an instantaneous equivalent. Instantaneous acceleration is going to be the derivative of velocity with respect to time. Again, same units, meters per second squared. Now, there's two types of acceleration. Uniform acceleration, which is when it's constant. That's what we need in this for this formula to work. And then there's also non-uniform acceleration, where acceleration is not constant. So we'll get into both of those in the next few videos. One last thing we need to touch on before going to the practice problems is the relationship between these. We took calculus. We know what derivatives and integrals are. So derivative, integral. Derivative is the rate of change of function, also known as the slope of the tangent line of that function. Integral is the area under the curve of that function, area under the graph. And so both of these are at play here. We know that velocity is the derivative of position and acceleration is the derivative of velocity. And so the derivative pathway is going to be position to velocity to acceleration. The derivative of position is velocity and so on. For integrals, it's going to be the opposite. It's going to be acceleration to velocity to position. The integral of acceleration is velocity and so on. Now, there's also the graphical implications of this, and we're going to mention that in the practice problems in a second. I'll show you what that means exactly. Because we know the derivative is the slope of a tangent line and integral's area under the curve. Those are graphical equivalents. So let's get into the practice problem, and I'll show you what I mean. So we only have 2 practice problems today. It's usually going to be 3, but this is the first lesson, so we didn't really go over that much. So first practice problem. Car travels in the positive x direction for the first 5 seconds. So we're given a time interval, 5 seconds. The average velocity is 6.57 meters per second. We're given an average velocity. How far does the car travel? That's going to be displacement, change in position. And so what equation do we know that relates average velocity, displacement, and time interval? Well, that is the definition of average velocity is displacement over time interval. Now, how do we rearrange this so we can solve for displacement? Well, that's just a little bit of algebra. We get displacement is equal to average velocity times time. And now we plug in what we know. Average velocity is 6.57 meters per second. Do not forget units. I'm just not writing them on the screen because to save time. And time interval is 5.00, so we multiplied them together. Now, that brings up a good question. Are we allowed to use calculators? Most of the time, yes, because some of these calculations can be pretty difficult. So you're just going to do 6.57 times 5. It's not too bad, but, you know, when you got it, you can use it. So it's 32.85 meters is the unit for displacement. And so that's going to be your answer for the first problem. Okay, second problem is a graphical problem, like I promised. It says there's a physics professor leaving her house, walks, blah, blah, blah. It's just a description of her motion. Now, what it's saying is here's the graph of position versus time. XT graphs are position versus time. We're also going to deal with VT and AT in the future. VT is velocity versus time, AT is acceleration versus time. But for now, all we care about is this position versus time. Now, we know that the derivative of position is velocity, or the slope of the tangent line at any point is the instantaneous velocity of the professor. And so that's what we want. What we want when her velocity is any of these criteria. So when is it 0? That's when it's a horizontal tangent line, pretty much flat. And so that's going to be 0.4 right here. That looks about flat. And so that is when the velocity is 0. When the velocity is constant and positive. Well, from calculus, we know that if the derivative is constant and positive, that means that the actual graph itself is going to be linear and increasing. And what is that? Well, that looks like 0.1 right here. That's about a linear section of a graph, and it's increasing. So 0.1 is going to fit criteria B. For C, it's constant and negative, and so the graph is going to be linear and decreasing. Looks like 0.5 over here. That is linear, and that is decreasing. For D, increasing in magnitude. So if the velocity is increasing, if the derivative is increasing, that means that the original function is concave up. Looks like 0.2 because that's, you know, kind of curved upwards. And finally, decreasing in magnitude, if velocity is decreasing, that means the position is concave down. That, of course, is 0.3 over here. So this is just a basic analysis of the graph. We didn't really have to calculate any values from this. Just know that velocity is the derivative of position and what that means specifically. That's it for this first video. I know it's a bit shorter than usual unit videos because it is only a lesson video, but we just covered the basic kinematic variables and how they're related to each other. Next time, we're going to talk about kinematic equations and uniform acceleration.